So today I want to talk about a transmitter-receiver system. I sketched here a typical setup of a radio link. We have a data source, which in principle is fed to our transmitter, and one essential part of our transmitter is the last stage, the power amplifier. And this power amplifier will feed a power P1 to the antenna. And at a certain distance R, there we will have the receiving antenna, which in principle receives a power P2, which is fed normally in the first stage of a receiver, which is a low noise amplifier, and then after demodulation the data is given to the data sink. The problem is now how to describe these systems of antennas, transmitting antenna and receiving antenna. In principle, you see, if we enhance the distance, it's you can imagine that the received power will drop with increasing distance. But on the other hand, we have here a low noise amplifier, and as long as we increase the amplification, we could again increase the power P2 to a certain level so that we can demodulate the signal. The problem is now that here in this setup is a certain element missing, because in each receiver will add a certain noise. And in the most cases this noise will be terminal noise. And the problem is now, if the power P2 drops beyond a certain level, it will disappear in the noise and we cannot recover the signal. So in the preceding considerations we will now look how we can describe this transmitter-receiver system in principle. So we must describe how the transmitting antenna transmits its power and how the receiving antenna is receiving its power, and in principle I will give you an idea about the ratio or about the terminal noise. What we cannot do is, of course, we cannot go or we cannot describe really the transmitting antenna or the receiving antenna with the help of Maxwell's equation. So we will set up smaller or easier models to describe the behavior of the transmitting and the receiving antenna. I now want to describe the transmitting antenna, but we want to describe the transmitting antenna without reference to Maxwell's equation, but we will set up a phenomenological theory. What does this mean? We assume that we have a so-called isotropic point radiator. This means we have a point in space, and from out of this point in space this point in space will emit a certain power P1. And if I assume that this power is isotropically radiated over the sphere, then we will get a certain power density, or the Poynting vector, which is given by P1 divided by the area of the sphere, which is given here by 4 pi r squared, where this is the radius r of our sphere. This means an isotropic point radiator radiates the power isotropically over a sphere, or over the area of the sphere, and this area of the sphere would be given by the 4πr squared. The problem is that this isotropic point radiator does not exist for electromagnetic radiation. The problem is that the real antennas in the electromagnetic antennas have a certain so-called radiation pattern, and we distinguish here for example, the main beam and, for example, the side loops. Of course, if we want to radiate to a certain, in the direction of the certain receiver, we will direct the main beam in the direction of the receiver, and we will describe the influence of the main beam by a value G1, which we call G1 is the gain of the transmitting antenna in the direction of the main beam. So in this direction, in the direction of the main beam, we will have a enhanced radiation S of R will then be described by G1 times P1 over 4 pi R squared. But this power density only resides in the direction of the main beam. So as I already explained before, in the direction of the main beam we have a certain gain, and so we can say that the radiated power density, which is radiated in the direction of the main beam, is given by this expression, and here we have the product G1 times P1, which is normally termed AERP, which comes from is created by the words effective isotropic radiated power. According to this equation, it seems that now the isotropic point radiator, instead of only radiating P1, it would radiate G1 times P1. But of course, this power density exists only in the direction of the main beam. I now want to discuss with you the behavior of a receiving antenna. So we saw that with the help of the transmitting antenna we can radiate a certain power, and of course normally the receiving antenna is very far away from the transmitting antenna, so we will have here the radiation power will be given in principle by a plane wave. This means that the radiation will be vertical to the direction of parallel to the direction of propagation, and we know that this power density would be now given by S of R. It's G1 P1 divided by 4 pi R squared. This means here we have a plane wave which will enter into the receiving antenna, and its easiest way to understand the behavior of the receiving antenna is if I start with a parabolic antenna. Of course, the parabolic antenna will in principle gather all the power which will flow in to its cross-section, so we can assign to this cross-section a certain area, AV2. We will call this is AV2 is the effective area of the receiving antenna, and now we can write for the received power P2, it just will be equal to the effective area of the receiving antenna times the power density S of R, or which will be equal to is equal to P2 times effective area of the receiving antenna times the gain of the transmitting antenna P1 divided by 4 pi r squared. This means with the help of this equation we in principle can now calculate the received power independent of the radiated power. One point which is not very nice here is that we now use two different terms to describe the antenna. One term would be the gain of the transmitting antenna, and one would be the effective area of the receiving antenna. But in the next step I will give you an equation which relates the two constances to each other. I now want to discuss the relation between a gain of the antenna and its effective area or effective aperture of the same antenna. So one can, on one side, see that according to the law of reciprocity, we will find if I take the transmitting antenna as receiving antenna and vice versa, we will see that AV1 divided by G1 must be equal to AV2 divided by G2, and we will see that this is constant. And now I must have a look on the Maxwell theory, but I only can give the result. And for an arbitrary antenna we will have that the relation between the effective area of the receiving antenna divided by its gain is given by lambda naught square divided by 4 pi. Of course, this I only can give now this result, and we will use this relation to give the equation for the received power as a function of the transmitted power. So up to now we set up the received power as a function of the transmitted power by this equation. This means we have here the received power, here the transmitted power, and to describe the antenna we use the gain of the transmitting antenna G1, the distance, and the effective aperture of the receiving antenna. But in the last step I showed you, or I gave you, according that we have, according to Maxwell's equation, the ratio of AB to G is given by lambda naught square divided by 4 pi. This is, of course, then also especially equal to, we can say, AV2 will be then lambda naught square divided by 4 pi times G2. So of course we can insert this equation into the equation for the received power. We will have then, this is lambda naught square divided by 4 pi times G2 times G1 times 4 pi r square times P1. And now we only use in principle the gain of the receiving antenna and the gain of the transmitting antenna to calculate the received power, and we will have that 2 pi, the P2, the received power, will be given by G2 times G1 divided by 4 pi r over lambda naught square times P1. So this equation now describes a transmitter-receiver system, at least the power P1 which is transmitted, and P2 will be the power which is received, and the the factor here is given. What we must know is the gain of the transmitting antenna, the gain of the receiving antenna, and of course we must use the distance here in this expression. And in the next step I will convert or discuss this also in a dB scale. I will now introduce the so-called link budget of a communication link. And we saw that this equation describes the received power as a function of the transmitted power. Normally in system calculation we use the so-called dB or dBm scale. And now I will use introduce my notation, what I use. For example, if I have a power, then the power is given in watt, but the dB scale use normally the logarithmic function. So I will introduce the power in dB, and I use the following notation. P with reference to dBm, or divided by dBm, is given as 10 times log the power P with reference to 1 milliwatt. So this equation makes in a mathematical sense no sense, because we use here P and here also the same value P, but on a physical base we can say, I can argue that in this equation I use the power in watt. Of course it will be, if I divide it by 1 milliwatt, it will have no dimension here anymore. And so I can convert it into the dB scale, or I can convert, for example, if I have the power given in dB, I must divide it by 10, and then I have to take it to the power of 10 times 1, perhaps I have to write it more here, again P divided by dBm divided by 10, and we have to take it to the power of 10, and we have to multiply it by 1 milliwatt, so we get here P again in the in milliwatt. So this is how we can convert the power given in dB into watt or milliwatt, and this is how we can convert the power which is given in watt to the dBm scale. This we will apply to our equation here, so we can say this is P2. We will write with reference to 1 milliwatt, it's given as G2 times G1 divided by 4 pi r over lambda naught square divided times P1. And if we, of course here I must divide by 1 milliwatt. And if we take the logarithm, then we can say 10 times log of P2 divided by 1 milliwatt is equal to, so you see, as soon as we take the logarithm of this expression, we will get, this is 10 times log G2 plus 10 times log G1 minus 20 times log 4 pi r over lambda naught plus 10 times log of P1 divided by 1 milliwatt. So this expression now, of course, will be equal to P2 in dBm. This, we will say this is G2 divided by dB. This is equal to, or this corresponds to G1 divided by dB, and this corresponds to, we will say this is minus L divided by dB, and this corresponds to P1 divided by dBm. So we come now to the equation, to the so-called link budget. Then the link budget would read P2 divided by dBm is given as G2 divided by dB plus G1 divided by dB minus L divided by dB plus P1 divided by dBm. This would be the link budget. And from this equation we see that L divided by dB is given by 20 log of 4 pi over r over lambda naught, and this is called the path loss. This means now, as soon as you convert this equation into a dB scale, you will get a very simple equation, and this equation is called the link budget of a communication link. Unfortunately, I don't have the time to discuss the terminal noise in detail, so I just can give you here some expressions. So one of the most disturbing factors in communication links is terminal noise, and as the term already tells you, the terminal noise depends on the absolute temperature, and we will use here normally a temperature, or assume a temperature of T round about 290 Kelvin, and then you can calculate the available noise power in dBm, and there is the noise power N in dBm is given as minus 174 plus 10 times log B with reference to 1 Hertz, and we see here B, this is the bandwidth, or I call it system bandwidth, which this means the terminal noise power will increase with the system bandwidth. So in a receiver system we had here the transmitting antenna, here we had the power P2, and in the simplest case I assume here that the noise is added to the system, and this noise power now is given by in dBm. So normally we will define the so-called signal to noise ratio, or it's called SNR. This is the received power P2 with reference to the noise which is fed into our system depending on the noise bandwidth and the absolute power and the absolute temperature. Of course, the absolute temperature will determine this value. Of course, we can also convert the signal to noise ratio 2 dB. This means we'd have to take 10 times log of SNR, and this is then 10 times log P2 with reference to 1 milliwatt minus 10 times log the noise in dBm. Oh, sorry, the noise also with reference to 1 milliwatt. This means we multiply here with 1 milliwatt and here with 1 milliwatt before we can take the logarithm, and we get that SNR given in dB is then equal to P2 given in dBm minus N also given in dBm. This means with the help of this equation we can determine the signal to noise ratio which we will reach in the receiver, and for certain modulation schemes you must have certain signal to noise ratio so that the communication link can work.